In this video, let's understand DAG and three address code. DAG is also called as directed acyclic graph. It identifies common sub-expression. When you represent a DAG for any given expression, leaves represent operands and interior nodes are operators. Okay, so if I give you all any expression, say A plus A plus A, if I want to represent this expression in the form of syntax tree, I'll create node for A plus A and then this A as. So this is syntax tree representation of this expression. Now if I want to represent this expression in the form of DAG, okay, we need to identify the common expressions. Okay, since A is present thrice here, same expression is present thrice. What we can do is we can compute one expression just once. The one expression which is common, you can evaluate it just once and reuse it wherever required in that expression. Okay, so if I create a node for A, okay, now plus A is present. So instead of creating one more node for A, I'll make use of same reference of this node. Okay, so what I'll do is I'll take one link from here, put a plus and get one more link to this A, which will give me A plus A. Now A plus A value is at this point, value of A plus A. Now we have one more plus A here. So what I'll do is from this point, I'll create one more link, put a plus, and from here I'll get this link back to this A. Okay, this is DAG representation for any given expression. Let me give you all one more example. Say if I give you all A plus B into A plus B. Now remember, whenever arithmetic expressions are given, parenthesized expressions have got highest precedence. Okay, so in this case, A plus B is given inside parenthesis. Even this A plus B is given inside parenthesis. So we evaluate this first and then perform multiplication. So if I want to represent a syntax tree for this, I'll create node for A plus B. I'll create node for this A plus B and then join these two by star. If I want to represent this by using DAG, then in that case, I'll start with A plus B first. So A is encountered for the first time. I'll create node for B and I'll join this by plus. Now, there is one more A plus B and it is same expression, right? So instead of creating new nodes for A and B, A plus B computation is there at this point. But I need multiplied by one more A plus B. So from here, I'll take one link out, put a star here and then again come back to this point. So this is A plus B into A plus B. Fine. So this is how a DAG is represented for this expression. There is one more method of representing a DAG for given expressions, that is by using three address code. Okay, that method we'll see once I cover three address code. Okay, so let's continue with three address code. So three address code is built from two concepts, addresses and instructions. Addresses can be name, constant and temporaries. Okay, so say if I give a statement as x plus y into z. If I want to generate three address statement for this, three address code for this expression, okay, some rules for three address code statements. Every statement in three address code can have at most three addresses, that is at most three variables. You cannot have more than two operators. Okay, you can just have one operator in three address code statement. Fine. So there are some valid three address code statements. Okay, so let's see different types. The first one is assignment statement. Okay, assignment statement which can be of the form x is equal to y operator z, or you can have x is equal to op y. Okay, so this is any operator in between, only one operator. Over here it can be unary operators. Fine. So second one, we can have valid copy statements, that is say x is equal to y. Okay. Third one is unconditional jump. Okay, so whenever we are generating three address code for some constructs, okay, you will encounter this go to statement. Okay, so we can have go to and some label. Okay, so control flow goes to statement labeled L, okay, without checking any condition. Okay, that's why it is called as unconditional. Then we can have conditional statement. Conditional statement, that is, say if we are checking for certain condition, if X relational operator Y go to some label. Okay, so you're checking for condition and then you jump to this label. Okay, then we can have procedure call. Okay, procedure call wherein we write the parameters first, say parameter x1, parameter x2. So these are two parameters for that function, and call p comma n indicates that this p is procedure name, comma n stands for number of parameters. So if number of parameters in your procedure call are 2, the code is call procedure name comma 2. Right? Then we can have array references, 3 address code statement for array, which can be of the form x is equal to y of I or y of I is equal to x. Okay, some statements of this form for array references. And finally we can have some address and pointer assignment. Okay, address and pointer assignment. So you can have statements like x is equal to and y, x is equal to star y, and star x is equal to y. So these are some of the types of 3 address code statements. Now next we'll see implementation of 3 address code. Okay, so if I write 3 address code for any given expression, how that code can be represented in the form of some fields. Okay, and these representations are, the first one is quadruples, second one is triples, and third one is indirect triples. Okay, so given any arithmetic expression, we can write 3 address code for that expression and then represent each of the 3 address statement in the form of quadruples, triples, and indirect triples. So let's take one example of this. Say if I give you all an expression as x is equal to minus a into b plus minus a into b. Okay, so how do we write 3 address code statement for this expression? As we've already seen different types of 3 address code statements according to the priority. In this case, unary operators have got highest precedence. After that you can perform multiplication, then plus, and then assignment. Okay, so I'll create a temporary t1 which will store this computation u minus. Okay, I represent unary minus as u minus and a. Okay, then multiplied by b. So t2 is equal to, I take t1 into b. Okay, then t3 is equal to unary minus a. T4 is equal to T3 into B. Okay, so we have computed this, we have computed this. Then T5 is equal to, this value is there in T2 and this value is there in T4. So it is T2 plus T4. Fine. So this is 3 address code. And then finally, once this evaluation is done, you just write x is equal to T5. So these are 3 address code statements for this expression. Now remember one thing. When you write 3 address code over here, you will say that this minus a into b and this minus a into b is common sub expression. Right now in unit 3, we are not dealing with optimization part. Okay, so DAG is actually there for you all in unit 4. Okay, so when you are generating this code, 3 address code, even if the expressions are common, you have to generate code for those expressions again. Okay, so if you note here, I have generated code for minus a into b twice. Okay, so you are supposed to generate code twice even if the expressions are repeating. Fine. So this is 3 address code. Okay, for this expression. Now once 3 address code is generated, we represent this code in the form of quadruples, triples, and indirect triples. Okay, so what is the meaning of quadruples? If you want to represent every 3 address code statement in the form of quadruples, quadra means 4. Okay, so you will have 4 components: operator, argument 1, argument 2, and result. Okay, so this is quadruples representation. Quadruples. Okay, so you consider every 3 address statement and then you represent that statement in the form of these 4 components. Okay, so the first one is T1 is equal to U minus A. So in this statement, what is the operator? It is U minus. So I'll write U minus under OP. Argument 1 is A. Argument 2 is dash, it is nothing, and the result of this is stored in T1. Consider the next statement, T2 is equal to T1 into B. Operator is star. Argument 1 is T1, argument 2 is B, and the result is stored in T2. So T2 comes here. Consider the third statement, operator is U minus, argument 1 is A, argument 2 is dash, and result is stored in T3. T4 is equal to T3 into B, operator is star, argument 1 is T3, argument 2 is B, and the result is stored in T4. Next, T5 is equal to T2 plus T4, operator is plus, argument 1 is T2, argument 2 is T4, and the result is stored in T5. And finally, X is equal to T5. Assignment statement. So operator is equal to, argument 1 is T5, and the result is stored in X. Okay, this is dash. And this is quadruple's representation of 3 address code statements. The next representation is triples representation, wherein there are only 3 arguments. Okay, so we avoid this result and we store some references to this computations. Okay, so we have operator, argument 1 and argument 2. Okay, references to temporaries are stored. Okay, instead of storing this temporary, we store the references. Fine, for temporaries which are created here. Okay, so for the first statement, I'll give reference as 0. So consider this statement. What is the operator? Operator is U minus. Argument 1 is A, argument 2 is dash. Okay, then 1, T2 is equal to T1 into B. Okay, so what is the operator? Operator is star. Argument 1 is temporary T1. Okay, now temporary T1 is computed at which point? Here, right? What is the reference? Reference is 0. So you place 0 over here and argument 2 is B. Fine. Consider the third statement. T3 is equal to U minus A. So I'll number this statement as 2. Operator is U minus. Argument 1 is A and argument 2 is dash. Then 3. Next statement is T4 is equal to T3 into B. So operator is star. Argument 1 is T3. T3 is computed at which point? It's over here, right? And what is the reference? 2. So argument 1 is 2 and argument 2 is B. Fine. Then next one, 4 is T5 is equal to T2 plus 4. So operator is plus. This temporary is generated at this statement, that is 1. So okay, I put that reference. And T4 is generated at this point, that is 3. Okay, so I'll write references of 1 and 3. And finally, you have X is equal to T5. Okay, so in this case, I'll just number this as 5. Okay, operator is equal to 5. Argument 1 is X. Okay, argument 1 is X and argument 2 is T5. T5 is computed at which point? 4. Okay, so when you write triples representation, please make a note of this, that there is a difference between quadruples and triples. When you're considering it for quadruples, X is equal to T5, operator is equal to, argument 1 is T5 and the result is stored in X. Since result is not present here, we consider X as argument 1 and argument 2, that is T5, is computed at this point. So this reference is stored over here. Okay, now next is indirect triples, wherein we just list pointers to triple. Okay, so I'll just create some addresses 11, 12, 13, the number of statements, and you just write 0. These are references 0, 1, 2, 3, 4, 5. Okay, that is number of statements here. How many statements are there? 0, 1, 2, 3, 4, 5. Okay, so first write those 0, 1, 2, 3, 4, 5 and put this values. Okay, this is indirect triple representation. Indirect triple representation.